Hello and welcome to this vSuite version 0.7 video tutorial, and in this video tutorial I'm going to cover a new component of the vSuite. This component has only just been committed to the vSuite GitHub master branch, so you'll need a version of the master branch as of today to use this new component. So to go along with Livy for lighting analysis, and NV for energy analysis, and FlowV for flow analysis, we now have AuVi for acoustic analysis. AuVi basically represents a front end to the excellent Python library pyroomacoustics. So a lot of the options in AuVi relate directly to the options in pyroomacoustics. And I will put a link to the pyroomacoustics GitHub in the associated, or the blog post which is associated with this video. And I'll put a link to the blog post in the video description. So AuVi will allow us to calculate impulse responses. We can convolve anechoic audio based on those impulse responses, and also reverberation times for a space that we model. And like with many components in a vSuite, that space that we model requires geometry and it requires materiality. So I have here two rooms connected by a corridor in the middle. And I'm just going to switch over to solid shading mode for this model. I've got some barrel vaulted ceilings, but otherwise rectilinear rooms, connecting corridor. But you can see that they have different colors in some places. And these colors represent the materials that I've associated with different faces of the model. In terms of geometry itself, we want only sort of planar geometry. We don't want any wall thickness or depth. We just want surfaces that describe the interior surfaces of the space. And we want those surfaces that make up the interior surfaces of the space to completely wrap the volume, and we want the normals, which are indicated by these blue lines here, we want the normals to point outwards in all cases. And ideally the geometry should be manifold. So if you don't know what manifold means in this context, then you can check up what Blender means by manifold. So that's sort of the bare bones of the geometry that we want, the shape that we want of the space. We can also apply materials to each of these faces, and these materials will describe the acoustic qualities of the surfaces themselves. So for example, if I come into my material properties tab, you can see here the list of materials I've got associated with this or these two rooms. So for example, we can see that this brick vault material is applied to both ceilings. We can see that this concrete material is applied to the walls of this room. We can see that this ply material is applied to the walls of this room. So every surface that you use to encompass the volume of the space should have a material associated with it, or really must have a material associated with it. And that material can have acoustic qualities. And these acoustic qualities are set within the vSuite material section of the material panel for that currently selected material, in this case concrete. So now in the vSuite material section, instead of the default geometry or light sensor or FlowV boundary, we select AuVi material. And once we've selected AuVi material, we then have the choice for the acoustic absorption coefficients of that material to set either database or custom. If it's database, then we can then pick a material class. So I've got massive constructions and hard surfaces for this concrete at the moment. And within that, I've got the unpainted concrete material. This database, by the way, is the one that comes from pyroomacoustics and is included with the V Suite. As of the making of this video, you can't, through the interface, create new entries in this database. That will follow at some point in the future. But as well as database, we can select custom, and we can now specify manually sound absorption coefficients for this material. If we pick flat response, then we can select one sound absorption coefficient for all octave bands. And if we turn that off, we can select an absorption coefficient for all the octave bands. Everything in AuVi is done at 16 kilohertz. So, and at 16 kilohertz, we have 7 octave bands running up to 8,000 hertz mid-center band. But I'm just going to stick with database for this concrete material. We also have in AuVi and pyroomacoustics, we can also use, as well as an image-based method to deal with early reflections, we can use a ray tracing method to better deal with late reflections. And that ray tracing method can use what's called a scatter coefficient, which describes how much the sound is scattered from a surface and is there to represent any non-modeled geometrical complexity or roughness. So for example, we've got here brick. This is rough brick, but I'm only modeling it as planar surfaces. So these scatter coefficients are there to mimic how the roughness of the brick, the geometric roughness of the brick, increases the scattering of the sound waves that hits it. So I can again pick custom or database for sound scattering coefficient. Here for the concrete, I've just got a flat response of 0.5. But again, if I turn off flat response, I can set a scattering coefficient for each octave band. If we come to the brick, then I've got scattering coefficients set for each octave band. And here, as is typical, scattering coefficient tends to go up with frequency. As the wavelength of the sound gets smaller, then any particular surface perturbation or surface roughness will increase the scattering of that sound. So as we go up in frequency, scattering coefficient tends to go up. So absorption coefficients, scattering coefficients are the two acoustic properties that we associate with each of the materials associated with each of the surfaces that encompass our volume. So that's the basics of the geometry and the materiality that we need. We also need a couple of other things. We need sources of sound and we need listeners of sound. Now, sources of sound are set by creating in Blender an empty. And we can add empties by going to add empty. And you can pick whatever sort of visual designation they have. They're all the same. And these empties can then, within the object properties panel, under V Suite object, be given the AuVi type source or AuVi type listener. So this is a source, so it's given the source type. This one over here is a listener, it's given the listener type. This one over here is another source, given a source type. And over here we have another listener. Now, because of the material properties I've given to these two different spaces, which are a little bit different, we've got concrete walls here, and we've got a plywood-based wall absorber here. This will then be the more reverberant space, or we would expect it to be the more reverberant space, and this is the less reverberant space. So I've called here this one source reverb, listener reverb, source quiet, and a listener quiet. So sources can only be specified by empties. Listeners can be specified by empty, and they can also be specified one other way. So if I come back maybe into solid mode, and I make this object just wireframe again, so we can look at this plane here. We've got two of them, one for each room, and each plane has been subdivided, and we can use the normal vSuite gridify option here if we want to subdivide our planes with a certain grid resolution. But these planes, we can also specify a listener at the center point of each of these planes. And we do that by associating with these two planes a material, and that material, I've just called it sensor here, that material is given the light sensor material type. So at this early stage of the AuVi implementation, I'm borrowing quite a lot of the infrastructure from Livy. So for the moment, we're just using the light sensor designation, which we would use for Livy, to specify that these two planes and the center point of the faces within those planes are listening points for AuVi. If I just look at the normals here, the normals point upwards, which is what we would require for a Livy simulation. In AuVi, the normal direction doesn't matter in terms of the numbers that we generate, but when we do visualization later on, our visualization plane is offset from our base plane in the direction of the normal. So it's generally a good idea to have the normals pointing upwards. So we have geometry, materiality, we have some sources, and we have some listeners specified by empties and by geometry. So we have everything now that we need to do a simulation. So I'll come down to my vSuite node tree, which is our main vSuite nodes sort of overall node tree. And I'm going to need an AuVi simulation node. And this can be added with the Add Analysis Nodes AuVi Simulation menu. So the AuVi simulation nodes set some of the parameters for the AuVi simulation. And like I said before, this relates largely to options within pyroomacoustics. So I could set animated here, and I can use this to do a parametric analysis. So I could set up a Blender animation across a number of Blender frames that might change, for example, the materials or some of the coefficients of the materials. Or I could change the shape of the rooms and the geometry across different frames and animate that within Blender. And then I would do a simulation here for each of those scenarios covered by these frames. But to keep things quick here, I'm going to turn off animated, and I'm just going to do a static analysis. Max order refers to the image-based method that pyroomacoustics uses for early reflections. The larger the order, the larger the number of source images we create. So I'm just using one here. That's the sort of lowest practical value. The lower the number, the quicker the simulation, and I want the simulation to stay relatively quick in this video. So I'm sticking to 1. You can go up to 3. 3 is kind of a good, accurate value, but 3, especially with very complex geometry, can create very long simulation times. And there's a reason why you might want to avoid that, which I'll cover in a moment. So I'm just going to stick to max order 1. RT rays, kind of similar. The lower the number, the quicker the simulation. Higher the number, potentially the more accurate your results. 1000 is a sort of minimum baseline, I think. And again, going higher, longer simulation times, you can go to 5,000, 10,000, 20,000. And receiver radius. This is the radius around each listener point that we collect rays over. So the default is 0.5 meters. So in effect, we're creating a sphere of radius 0.5 meters around each listener that we have to collect 1,000 rays over. So the smaller the radius, the smaller the sphere, the longer it takes to collect 1,000 rays. So again, lowering this number will increase simulation time, but can increase your positional accuracy of your results. So, but they're all fine for me for the purposes of this video. So I'm going to press Generate IR. IR standing for impulse response in this case. And we'll see that we get a Kiwi window pop up, but only on Linux and OS X. And although we can't monitor the progress of the simulation, the Kiwi window does present a cancel button, which will cancel the simulation. This window does not appear on Windows. And the only way you can stop the simulation is to shut down Blender and possibly forcibly have to quit Blender. So on Windows especially, these parameters are very important. If you pick, I don't know, 5 here, and you have very complex geometry, the simulation can take a very, very long time. And on Windows, you'll get no window to cancel the simulation, and you'll get no monitoring of the progress of the simulation. So it's better, I think, to start low with these numbers or start high with this number, and then slowly sort of increase your accuracy and increase your simulation time. So you get a feel for how long the simulation is going to take. But my Kiwi window has disappeared. That simulation has finished. And now I can start to work with the results. So the first thing I'll do is I'm going to connect the IR socket, impulse response socket of the AuVi simulation node, to the AuVi convolve node. Now the AuVi convolve node can be found in the Add Output Nodes AuVi convolve menu. And the AuVi convolve node does what is, for me at least, my favorite bit of AuVi, in that it will take an anechoic recording, so a recording that's been made without any echo, and I will put some links to anechoic sound sources in the blog post associated with this video. But you can get hold of an anechoic audio recording, which must be in WAV format, and you can process that anechoic recording to make it sound as if you were in this space, as if you were positioned at one of these two listener points. This convolve process only works for listeners that have been defined by empties. It doesn't work for listeners that have been defined by simulation planes. So I can select a WAV file. So I might select, for example, a speech file, and then I can play that.
Sound is all around us. It forms a crucial part of the way we interact with the world.
So if you're listening to this video on headphones, then you will have heard that sound without any reverberation. Obviously, if you're listening to this video in a reverberant space, then you're going to get the reverberation associated with that space. So it might be best to listen to this section with headphones. So that
sound is all around us.
Is the anechoic sound without echo. Now in this IR menu here, once I've connected my AuVi simulation node, this IR menu will give you or allow you to select the source listener pair that we're going to convolve this audio over. So if I select listener quiet, source quiet, that means in effect this anechoic sound is being played from here, and I'm going to listen to it, or I'm going to listen to the sound as if I listen to it here. And bear in mind that this is the room with my acoustic plywood panels. So this is a sort of relatively non-reverberant space. So once I've selected that, I can convolve, and now I can play this original sound source as it would sound played from here and listen to from here.
Sound is all around us. It forms a crucial part of the way we...
And I'll play the original again.
Sound is all around us.
So you'll notice a little drop in volume, because when I play the anechoic, it's kind of like you're here. You're listening to the raw sound. When I'm listening to the convolved, I'm listening to the sound over here. So I'm a little bit distant from the original sound source. And I'm not getting much reflection from the space because this is a relatively non-reverberant space. And you'll notice when I play the convolved sound,
sound is all around us.
There's no great sense of echo. There's a little bit, I think you can tell, but there's no great sense of echo. If I come over to my listener reverb source, reverb pair, so now I'm playing the sound from here and I'm listening to it here in my reverberant room. Press convolve again.
Sound is all around us. It forms a crucial part of the way we interact with the world.
Play the original again.
Sound is all around us. Sound is all around us.
So I think it's pretty clear now that we're getting the additional echo, the additional reverberation from this space, which has concrete walls, rather than this space, which has plywood sound absorbing walls. So that, I think, is a really nice way to sort of experience acoustically the space that you're designing. We could have played the sound here and listened to it here.
Sound is all around us.
So we're picking up some of the reverb from this space, but obviously now it's much quieter because the original sound is being played in a separate room, etc. So that's quite a nice thing to play with, I think. And we can pick something, percussion is quite good for picking out changes in reverberation time. So I could pick out this little drum sound here. Pretty dry, put it in my reverb space, and now it bangs a little bit. So have fun with that. And in addition to sort of processing these impulse responses, we can connect the VI results node to a VI chart node. And again, just for the listeners specified by empties, we can plot, so let's pick the reverb one. We can plot the room impulse response. So we can see that's the one for the reverberant room. We can pick the quiet room, and we can look at the impulse responses we're generating from those rooms. And we can also connect that VI results socket to the VI metrics node. And if we pick acoustics here, then again, for each of our for each of our empty derived source listener pairs, we can look at the reverberation time as calculated from that impulse response. And we can also connect a VI CSV node to this VI results node to output data to a CSV file. So I think that's all the kind of nodes that are relevant for AuVi simulation. We also have, because I specified listeners from this subdivided mesh in these two rooms, in the vSuite display tab, we also have this acoustics display button, which will pop up after a simulation. So I can hit that and I can now visualize the reverberation times for each of those mesh faces. And we can do the usual. This is all very similar to AuVi, this part of it, so we can visualize the results in different ways, and we can change our colors and etc. etc. I won't go into this because that's all been covered in sort of associated Livy videos. I think also shadow mapping and sky view factor also uses this same framework. The only difference when we're doing an acoustic display is this source menu, and this tells us what source we're looking at. So this represents all the listener points. So what reverberation time are we plotting, from this source or from this source? So at the moment we're plotting source reverb, but we can also plot source quiet. So from the source quiet, very low reverberation time in here. But as soon as sound from here does make it into this room, then that sound bounces around this room much more. So again, we can plot out the reverberation times for each of those individual points. So I think that's everything I have to cover here. I've updated the user manual to cover AuVi, and that's available on the main website now. And again, I'll provide the link to the blog post and the blog website in this video description. And I really do think that's everything I have to cover. Okay, thanks for watching.